Hello students. So we have started chapter number 5, which is about 2 degree of freedom, actually multi-degree of freedom system, and we derived the equation for multi-degree of freedom vibration of multi-degree of freedom system, actually for the 2 degree of freedom system, and we also solved it for the free vibration when there is no force. Okay, so we looked at the eigenvalues, the eigenvector which are associated with the solution. Okay, so we will come back to those things again, but let's first talk about the force vibration of those systems. The same system, if we apply a force now, how the solution will look like, which is easy basically. And after that we will continue with the meaning of all the eigenvectors, eigenvalues and all those things. So that makes it very interesting. But before that, let's solve the force vibration. So let's draw the system that we have been studying. So this is undamped system. It has two springs having a stiffness K1 and K2, two masses having mass M1 and M2, like this one. Okay, and we have two variables, x1 here, x2 there, and we found out the equation that we found out last time. Look like this one, M1 0 0 M2. Okay, and then it had x1 double dot, x2 double dot, then we had plus, then we had k1 plus k2 minus k2 minus k2, then k2. Yeah, so this is k1, this is k2 basically. Yeah, okay. And we had x1 and x2 here, and equal to 0 for the free vibration. However, we have equal to f naught sine omega t. So we say harmonic force. So if f equal to f naught sine omega t is given, then the t term, this is degree of freedom system 1, this is 2, and force is applied to degree of freedom system 2, hence the value will be 0, and here it will be f naught sine omega t. So this will be the equation. Yeah. So the first row corresponds to the first equation regarding the M1, the second row corresponds to the second one, and you can see that second one only has the force applied, hence you have the force given here. If you had some force applied here also, then you can also write there will be another force term, the term here. Let us say we have F1 cos omega t, you can also write F1 cos omega t there. Right? So you can also have that, but let's talk about just this one. You applied a force F at this one. Okay, now this is the general, this equation basically thus corresponds to this particular system only. We can also write in general terms. Okay, instead of writing k1 plus k2 minus like this one, we can say this whole thing as k11, we can say like that, right? So, and this is k12, we can write this one, we can say k21, this we can say k22, like this one. Yeah, so this is also, we call this as mass matrix. Okay, mass matrix. This is a stiffness matrix. Yeah, a stiffness matrix. Okay, you should notice here that mass matrix is symmetric. Yeah, you can see that this is symmetric, right? So meaning that whatever this symmetric about the diagonal basically. Similarly here, this is also symmetric. Symmetric means the transpose of this matrix is equal to the matrix itself. So if you take transpose of this, you will get the same matrix. Yeah. So in both of them are symmetric. So this will help later on. So just remember, this is symmetric matrices. So symmetric matrices have some properties, and we can use those properties later on. Okay. So when we are trying to understand the meaning of eigenvectors and what we can do, some orthogonality of the eigenvectors and all. Okay, we will come back to that later on. But right now, what I mean to say is, the same equation, we can just write it as M11, 0, 0, M22, yeah, like this one. In this case, even I can have just M1 only, right, M1 only and M2, okay, and then we have x1 double dot, x2 double dot, and plus, here we write k11, k12, k21, k22, okay, and then we have x1, x2, and this is equal to, here also we can have, instead of here, we can have here, also we can do that, right? So this is, we are writing general 2 degree of freedom system, right? General 2 degree of freedom system we want to study basically, and hence we are writing this one, right? So let us say, forget about this system, we are not talking about this system. There is another, this general system, okay, so which has a 2 degree of freedom system, M1, M2. These are the two displacements, x1 and x2, but this is the second derivative of those, so these are accretion terms, here they are displacement terms, and this we have to solve basically, this we want, yeah. So in the meaning of this basically is force is not applied here, yeah, rather force is applied here, right? You can also apply the force here also, right? So F equal to F naught sine omega t, if you are saying, so is it the same thing? Either you can apply force here, or you can apply force here, or you can apply force both of the places, but this is a general system we want to solve. Yeah, so this system also given in your book, and hence I choose this one, okay, so that you can also relate. You can go back to the book also and see how it is solved here. So we have a system to solve, and the system is M1, then you have zero, then M0 again, 0, then M2, and you have x1 double dot, x2 double dot, okay, and then plus we have k11, k12, k21, and k22, yeah. So and then we have x1, x2, and we have f naught sine omega t 0, right? So this is general 2 degree of freedom system. You want to solve it. Given this force, we assume that force will be of the, like if force is like this one, again we are not interested in the free vibration term here, so transient term, but because of the free vibration, which will be eventually, that will die out basically. What will remain here is the steady state term, yes, or particular integral term, right? So particular solution. So here solution, we can assume that our solution is x1, x2 is equal to big X1, X2, and then we have sine omega t. So this will be the solution. Yeah. So for 1 degree of freedom system also we have seen basically. So when the force is of this type, solution is also this type. Okay. There is not even a phase difference, because you know the phase difference comes because of the damper. This is a free vibration, not free, undamped vibration problem. Hence there is a no phi or phi equal to 0. So solution will be like this. Next thing is we are going to just differentiate, double differentiation. You get x1, x2 dot will be equal to x1, x2, and then you have minus here, minus omega square and sine omega t. So okay, now we'll put both the things here and we see how it will work out. What we can see here is this one becomes, this is x1 and x2 only. So what we will get here is like this. The equation we will get is k11 minus m1 omega square. Yeah. Then we have k. Then we have k12. We have k21. Then we have k22 minus m2 omega square. So we have this term multiplied by, we'll have x1, x2 here. Yeah, is equal to, we will get f0 and 0 here. Why? Because we also have the sine omega t terms here, sine omega t terms here, both will be cancelled. So finally we will have this one. So this is like, there is one matrix multiplied by a vector equal to a vector. Now we have to solve it. How will you solve? Okay, it is something like this matrix. This matrix, we have to invert in order to find out. So if I find out x1, x2, so x1, x2 will be equal to inverse of that matrix, right? So inverse of that matrix is k11 minus m1 omega square, k12, k21, k22 minus m2 omega square. Inverse of that multiplied by f0 is 0. So that's, we will have that. Okay. Now we have to find out this one. Okay, so if you find out, then it will be the final solution. So let's find out. Okay, so in order to find out the inverse of that, what you have to do? Simply the inverse of that. So k11 minus m omega square, k12, k21 and k22 minus m2 omega square inverse will be equal to, it will be simply we will just interchange it. So we will have k22 minus m2 omega square, and here we will have k 11 minus m2, sorry, m1, this will be m1. So m1 omega square, and then these two terms will be negative. So here we will have minus k12 minus k21. Yeah, so that's what we will have. Yeah, so it goes like this. Yeah, okay. So it's done. Then divided by determinant of this term. Okay, so determinant of that. So k11 minus m1 omega square, k12, k21, k22 minus m2 omega square, right? You get like that. So now if that is the thing, first we have to find out what is the determinant of that. Okay, so determinant of this. Yeah, so determinant, let's write del here like this. The whole thing is determinant. So this is del basically. So this determinant del will equal to k1 minus m1 omega square multiplied by k22 minus m2 omega square minus k12 k21, right? Yeah, okay. So or equal to. Now, what do we see in this case? Basically, we also have to, we can invert this, we can also write this term in terms of the omega and omega 2, you know. So what are those omega 1 and omega 2? Omega 1 and omega 2 are the natural frequencies, the two natural frequencies. So for this case, we have to also find out what is the two natural frequency. As far as this is concerned, we already have x1 and x2. We can actually write this, and delta in any case we can find out in the present form. But it is a good idea to also write this a little bit differently, so that in terms of omega n, for example, for 1 degree of freedom system, we wrote this in terms of omega n. But in this case also we have omega n, but rather we have two natural frequency, omega 1 and omega 2. So in terms of that also we can write, so we will do that. So here what we will do is just make this k1 1 and k2 2 common. So hence we have like this 1 minus m1 over k11, sorry, okay, common, we will take out m1 times m2, so m1 times m2, so divide by m1 here, we get k11 over m1 minus omega square, and similarly here get k22 minus m2 minus omega square, minus we get here k1 to k21. Okay, now we have to find out, write this in terms of omega n. If we had omega n term here, we know that the determinant of this will be 0. What I mean to say, yesterday we find out that the if f naught is equal to 0, means for the case of free vibration, this without the inverse term. Okay, so free vibration, just right here. So for free vibration, what we got? We got like this: k11 minus m1 omega square. Okay, let's write omega n in this case, right? Omega k12, k21, and k22 minus m2 omega n square, right? Times x1, x2 was equal to 0 and 0, right? So, and hence, because of that, this was the determinant of that has to be equal to 0 when we have the natural frequency. Yeah, we have natural frequency that we have seen yesterday, right? So in the previous lecture, you can see that. Yeah. So if that is the case, that really means that we have this right here. Okay. So in that case, for when omega equal to omega n, delta is equal to 0. That we know. Yeah. Okay. So let's put that. So what we get? M1, then M2, K11 over M1 minus omega n square, K22 over M2 minus omega n square, minus K12, K21 equal to 0. That's right. Yeah. Okay. So simply in that case, we can find out that actually, if that is the case, then this term K12 times K21 is equal to this term, right? Equal to M1, M2, K11 over M1 minus omega n square multiplied by K22 over M2 minus omega n square. That's what you get. Mind you, this is omega n term, means omega n equal to omega 1 and omega 2. That is what is the meaning of that, right? Okay. So let's erase this one. and also this, so that we can write it further. So the equation, this delta, that really means this is a special case when delta equal to 0, when omega equal to omega n, you know. So okay, so what we get here is delta, original delta, this one, this delta will be equal to, so we have m1 m2 in common, and then we will have this term, that means k11 over m1 minus omega square, k22 over m2 over omega square, okay, and then we have minus this term, minus k12 over k21, k12 over m1 m2, so k12 times k21 divided by m1 m2, so we have this term, so we have k11 over m1 minus omega n square, then k22 over m2 minus omega n square, right? So we have this term, yeah. We can expand it further just to see what the expression we get. So equal to m1 m2, and we have this multiplied by this minus this multiplied by this, so you can see that automatically this term is basically taken care of, yeah. So let's expand it and see what happens. Okay, so let's expand. So from here we get k, so this multiplies by this one, the k11 over m1, k22 over m2, here also k11 over m1 multiplied by k22 over m2, they will cancel out, so we will not write it. Otherwise what we get is omega to the power 4, and then we have minus, okay, and then minus we have k11 over m1 plus k22 over m2, and then we have omega square term, and then this side we have similar term, so this is equal to, will be equal to minus omega n4, and then we have plus term, and we will have k11 over m1 plus k22 over m2 multiplied by omega n square. So we have like this. So let's simplify this further. So same delta here, we can write delta equal to, and then we have m1 m2, and then we can combine this term here, so we have omega 4 minus omega n4, okay, and then we have this term plus, so minus k11 over m1 plus k22 over m2, okay, and then we have omega square term here, and then we have minus omega n square term here. So we have combined this and this, and this and these are here, yeah. So we write like this. So next is you can m1 m2, this also you can expand something like this, omega square minus omega n square multiplied by omega square plus omega n square, like this, right? So minus we have k11 plus divided by m1 k22 over m2 omega square minus omega n square, yeah. Okay, so So next is equal to m1 m2, and then we have this common, right? Omega square minus omega n square. So we can write omega square minus omega n square common, and then we have omega square plus omega n square minus this term k11 over m1 plus k22 over m2. So this term. Okay, now you have to understand what is the meaning of this. Okay, now in order to understand this one, let's look at this the equation, right? So this means this equal to, we have this term m1 m2 multiplied by this in terms of omega n square. So if we had omega, if we had to find out omega n from here, how will it look like? So basically we write like this. This equation we wrote earlier, which relates, actually this is the quadratic equation. Here omega n you can write omega n equal to lambda. Yeah, so quadratic equation. So what do we get? If omega n equal to lambda, then you will get equation m1 m2 multiplied by here lambda square minus k11 over m1 plus k22 over m2 lambda, yeah, and then we'll have plus k11 over m1 multiplied by k22 over m2, like this. Yeah, so this, it will be something like this: k12 k21 when omega n square equal to lambda, omega n square equal to lambda. Okay, so it will be like this. Same equation, I am expanding it further. What we want to find out, we want to further simplify this one. For that we need to simplify here also. I mean, from here we will get a clue what is the meaning of that. So k11 1 to multiply by k21 equal to this one, or simply we get lambda square minus k11 over m1 plus k22 over m2 lambda, and then plus we can write k11 k22 over m1 m2 minus k21 k12 over m1 m2 equal to 0. So this is a quadratic term, yeah, and why this is a b term, right? Okay, so now lambda will be equal to minus this, so this will be k11 over m1 plus k22 over m2, yeah. This is a minus b term, so this is b, so minus b terms this, then plus minus root under something, right, over 2, right. There will be some value here. Let us say value is q. There is some q value. Yeah. Here there will be plus minus term here, right? So that means we can. This is lambda 1 2, lambda 1 comma 2 is equal to like this. Okay. Plus my root b square minus 4ac. So this square minus 4, this term, that represent that q value, because we don't need it actually, so that's why we are doing it. So what we see here, lambda 1 plus lambda 2, if you add them, then what would happen? This term will go plus or minus, this make it 0, and this is half, that will be k11 m1 plus k22 over m2. Okay, this is the thing we want to write it here. So here, then what is the meaning of that? Lambda 1, lambda 2. We assume that omega n square. So actually this becomes 1 square, omega 1 square, and this is omega 2 square, meaning that omega 1 square plus omega 2 square is equal to k11 over m1 plus k22 over m2. And that really means that here, since this is omega 1 square plus omega 2 square equal to k11 over m1 plus k22 over m2, here we can assume n here 1 and this will automatically will be 2. What meaning is m1 times m2 omega square minus omega 1 square. Let's call this one as omega 1 square. So this term omega 1 square, so omega n will be either omega 1 or omega 2. Let's assume here omega n equal to 1. Then what happens? Omega square, and then omega 1 square minus this omega 1 square minus this term, this is equal to minus omega 2 square. So this will be omega 2 square. Similarly, if you assume this omega n equal to omega 2, because omega n will be either omega 1 or omega 2. Yeah. So if you assume omega 2 n equal to 2, omega 2 square, then omega square plus omega 2 square minus k11 over m1 plus k22 over m2, and then you get omega 2 square minus k11 over m1 minus k22 over m2. Then this will go that side, will be minus omega 1 square. So it will be like this. That means this delta is equal to this. So we have to find out the final value of x1 and x2. Yeah, so this gives us just the determinant of the matrix. Yeah, so final we have x1 and x2 is equal to, okay, determinant this one. So we will have 1 over delta, which is equal to m1 m2 omega square minus omega 1 square omega square minus omega 2 square. Okay, so these are natural frequency, there are two natural frequency, and then we have the matrix. Matrix was, we had m2 k22, so k22 minus m2 omega square. Here we had the minus k21 minus k12, and here k11 minus m1 omega square. Yeah, and then here we have to write f naught and 0. That's what that is. Right? Okay, and now we can find out x1 and x2. Right? So our x1 will be equal to this. Simply we will have f naught times k22 minus m2 omega square divided by m1 m2 omega square minus omega 1 square omega square minus omega 2 square, and x2 will be equal to, so f0 here, so becomes minus f naught k12 divided by, okay, and same value here, m1 m2 multiplied by omega square omega 1 square multiplied omega square minus omega 2 square. So, and the final value, and x1 and x2 will be given by this value, which is given x1 and x2, and then we will have sine omega t given like that. So this is the solution of the forced vibration, meaning that 2 degree of freedom system, general 2 degree of freedom system. For that, the forced vibration problem, the amplitude is given by this one, and the x1, x2 is given by this one. And not to forget, this solution is for which equation? So as I said, this is for general 2 degree of freedom system. If the equation, this solution is valid when the equation looks like this, when equation is m1 0 0 m2, and here x1 double dot x2 double dot plus k11 k12 k21 k22, and here x1 x2 is equal to f naught sine omega t 0. Okay, if the system is this, if the problem is this one, then the solution is this one. Okay, so accordingly, the problem that we took last time, yesterday, that was it has k1 plus k2 here. So k11 equal to k1 plus k2 will be there. Yeah, so on. You have to write like that. Yeah. Okay. Similarly, if you have instead of the force instead of here, if you have here, then things will be again different. So what you get in that case, this term instead of k1 1 2, you will get k11 minus m1 omega square here, and here you will get k minus k1 2 1 term. Yeah, so it will the expression will look like differently basically. Yeah, so or in that case you can renumber also. We can also assume that the whatever you call the m1, you now calling m2. Automatically this will be written in the first row like that. In any way, it is very important that when you have this equation, okay, then only this solution is valid. Okay, so accordingly you have to know how to write x1 and x2. Okay. Now, although we have taken general equation as simplified one, we took the just diagonal m1 and m2. However, the equation could be also something like this one: m1, m11, m12, m21, m22. It could be also like this. Yeah. So x1 double dot, x2 double dot is plus we have k11, k12, k21, k22, and you have x1 and x2, and we are talking about the free vibration again. So we are going back to the free vibration because of some interesting property. As I said earlier, it has the eigenvectors. We have to understand basically in more details so that we can also have insight basically. Yeah. So what we see here, it is kind of coupling, right? So if m1 not m12, m21 equal to m12 not equal to 0, in that case what you see is there is a coupling basically, right? So this kind of coupling is going to dynamic coupling. Dynamic coupling. Yeah. Here also when k12 equal to k21 not equal to 0, yeah, so since it has the displacement term only and the spring is related to the static, right? So we call it static coupling or statically coupled, right? Static coupling. Okay. We are not talking about the damping yet. Okay. So it's again undamped 2 degree of freedom system, and we are talking about the free vibration. Okay. Now as I said earlier, like typically the spring, the stiffness matrix and mass matrix both will be symmetric, but this may be coupled. So symmetric meaning that M1 2 equal to M21. Most it will be like this, and here also K12 equal to K21 will be like that. Okay. Okay. So this one is this makes it symmetric, but still there may be coupling is there. It is not coupled when we have the diagonal term only. So let's say M11 0 0 M22 term, if we had like this, x1 double dot x2 double dot, plus here also we have K11 0 0 K22, and we have x1 x2 and equal to 0 0. What we see here, we can write two equations which are independent of each other. So we are going to uncouple them. So if you expand, the first equation will be M11 x1 double dot plus K11 x1 equal to 0, and second will be M22 x2 double dot plus K22 x2 equal to 0. See here x1 here, x1 here, there is no x1 in this case here, right? But in this case, if you write two equations, x1 and x2 will appear in both of them, but here they are totally uncoupled, so you call it uncoupled. What you see here is a two single degree of freedom system. So that means this equivalent of, actually you are having two systems. One system is here, you have K11, M11, and you have x1 here, x1 here, and then there is another system with K22 stiffness, mass M22 and x2. There are two different systems, but we are writing it together. That's what the meaning is. Yeah, and hence you will know that since they are not coupled, not related to each other, so it will have its own natural frequency. This will have its own natural frequency, but still we are writing in a matrix form, but they are uncoupled. That really means they are independent of each other. Means x1 is not influencing x2 and vice versa. Yeah? Okay. Okay, so now the question is, you have seen one equation which is coupled, there is another equation which is uncoupled. Okay. Now solving them is very easy. If you uncouple it, you can very easily solve. This becomes a linear differential equation of second order. That's it. There is no linear algebra involved anymore because they are uncoupled, right? Okay, so the question is it possible that this coupled equation, we somehow convert this equation into uncoupled equation? And that really means that how to make this matrix a diagonal matrix, right? So what to do that this matrix becomes a diagonal matrix and this also becomes a diagonal matrix, something like this one. And in that case, once we have that, then we can solve like this one, right? Very easily you can solve it. That will represent a two system basically. That question number one. Second question is, what can we understand if we have the diagonal from here, we convert into a diagonal system, like two independent system. So then what is the meaning of that? Okay. Here we can understand the meaning of this is there are separate two systems which will have different frequencies basically. This, if you do some operation and this, we will make two uncoupled equations. That means we will have two independent equations, two independent systems, and the two natural frequencies that we talked about in the last video, those two natural frequencies will represent these two systems basically. Yeah. So we will see what I'm saying. Okay, so what we will do is we will just write, instead of writing M1, M2 like this one, we will just write M cap. This is matrix M, this is matrix K, and from there we will go ahead. So a general equation will look like M x double dot plus K x equal to 0. Yeah? So 0 vector, x is also vector. Now from 2 degree of freedom, we are going to like a multi-degree of freedom system. So M will be n by n, right? K will be n by n matrix, and x will be n by 1, and this will be also n by 1, and here this will be n by 1 matrix, and this will be have n degrees of freedom. Meaning that now we are not limited to single degree of freedom system. This is multi-degree of freedom system. You can think about now we have many masses there, something like this, right? So like this, yeah, and then we have x1, x2, x3. This example is n equal to 3, but we have any number, n number of degrees of freedom, or n number, for example, in this case, n number of masses. You know, so this is M1, M2, M3, like this one. So then we will have we have to write this equation in terms of M will have all of them. M1, let us say this will be M1, 0, 0, 0, M2, 0. It could be like this one. Or M in general, we can also write it is as M11, M12, M13, right? For this, or any general, and so on. You can make 3 by 3 matrix like this one. So this is general mass matrix. Similarly, K also is general stiffness matrix. This x is equal to x1, x2, x3, x4 to xn, and x double dot is equal to x1 double dot, x2 double dot, x3 double dot, and so on till xn double dot, like this. And this is what the meaning of it. Yeah. And similarly, K will have K11, K12 till K1n, and then similarly here we will have Kn1, Kn2 till we have Knn, like this one. Similarly, M also we can general form, so this will go till M1n, and similarly it can go Mn1 and Mnn. Right? So we are talking about the multi-degree of freedom system, yeah, and this equation we are going to explore now, okay, so that we are not limited to degree of freedom system only. We have to actually apply to any number of degree of freedom system. Okay, so although this is the general purpose multi-degree of freedom system, we can write it like this one, but the solution remains the same. The solution in this case also will be x equal to, we write x naught and sine omega nt, right? Where omega n is a natural frequency. So we are expecting the solution will be x equal to x naught. This is also n by 1. This is also n by 1. Okay, this represents the amplitude. Yeah, so this x is variable, x naught is a constant, but constant vector and sine omega t. Now we have to find out the omega n there, right? Okay, so if we put it here, then this will be double. So this will be k, and then minus omega n square m, right? So this is what this will be, and x equal to 0. Yeah. So if you put this solution here, this is how it will be. Yeah, this we have seen for 2 degree of freedom system as well. Yeah. So x double dot, you take x double dot, So what do you get? X dot equal to minus omega n square x naught sine omega n t. You put x and x dot here and you will get this equation. Okay, not x, you will get x naught in this case, because x is will be equal to x naught sine omega n t, right? So you get x naught here. So x naught is also a vector here, right? So okay, now if that is the thing, then the determinant of k minus omega n square m has to equal to 0. Yeah, okay, we know why. This is because so that x naught has a non-trivial solution. Because of that, determinant of this has to be equal to 0, and this will give you omega n equal to omega 1, omega 2, omega 3 as omega 3 to till omega. Okay, so not to be confused with the number of let's call it m by 1 and like this. Yeah, so not to be confused with n for natural here, but this is okay. So till we get omega m. So this is m degree of freedom system. So it's right here. M degree of freedom. Yeah, okay. So omega n equal to omega 1, 2, 3 till m, because there is m degree of freedom system, and we will get by solving this one. So these are the natural frequencies. Okay. Now, and these are also the omega n squares are the eigenvalues, right? So eigenvalues, right? So this is omega 1 square, omega 2 square, omega 3 square to omega m square, all are eigenvalues. Corresponding eigenvector eigenvectors will come from x naught value, right? So we will have x naught 1, so x naught 1, x naught 2, x naught 3, and so on. We will have till x naught m. So this is the eigenvector. So for every eigenvalue there will be corresponding eigenvector, that we have seen for the case of two-degree of freedom system. We have seen, and what is the meaning of eigenvector. So these are associated, these and these are associated, right? And so on. These and these m, they are associated. So we get like this one. Okay. Now, if this is value, if this is the equation we are given, then there are some properties that we can find out. Okay, and the properties we are going to find out. The meaning of this is basically, put it here, if k minus omega 1 square m, and then you put x naught 1, then this is equal to 0. Yeah. Okay. And here we can multiply equal to 0. That really means if we multiply something else. So let's not write like this one. So k minus omega 1 square m x naught 1 equal to 0. Similarly, we can write k minus omega I square m and x naught ith 1 will be equal to 0. Yeah. And hence, if we multiply here x naught, let us say j term here, transpose of that will also be 0. So because this we are multiplying x naught j term, transpose and 0. Yeah, this will make a scalar number basically, so this is equal to 0. So here this one is 1 by n, this term is n by n, this is n by 1, so it's make it 1 by 1. So this is a scalar term. This one is n 1 by n, and this one is n by 1, so this becomes 1 by 1 finally, right? So 1 by 1, so a scalar, making a scalar. So what I did, the jth eigenvalue, the jth eigenvector, transpose of that multiplied by k minus omega I square m x naught ith eigenvector is equal to x naught j transpose 0, so all equal to 0. Similarly, we can interchange. Yeah, you can interchange and we can write similarly what it will be, x naught j transpose k minus omega j square m. Then here we will have, okay, let's write here. Okay, so first equation is this, second equation is interchanging I to j, so this becomes I transpose of that x naught, and then k minus omega j square m multiplied by x naught j is equal to x naught I transpose 0 is equal to 0. So we have two of them here. This is I here, j I here, and here we have x naught j. Okay, so let's call this one equation 1, this equation 2, and then from 1 minus 2, let us see what we get. Okay, so we will get this, we will get x naught I t0 k, and then we have x zero j minus, okay, so this minus this, so we have like this, xj minus xj term now, so here I then becomes j k x naught I, so we get this minus this term, okay, both k, then we will have minus, okay, minus, and then we have omega, so this minus this, yeah, so we have omega I square minus omega j term, square term, and then we'll have x naught I t m, and then we have x j, so this one is j term here, so okay, I j minus j I, so what actually we did is 2 minus I, okay, so it's 2 minus I, okay, so same thing, so I term here, then comes later on j, so we also have I term here, so m x, so j term here, okay. now that will be equal to this one. Why? Okay, so we are assuming that assuming what? Assuming M is symmetric. So x naught I T M x J transpose is equal to, you can interchange basically. So sorry, there is no transpose here like this. Yeah, just ith. So xi transpose of that, then m xj not transpose of that is equal to x naught I transpose m x naught, sorry, this will be j, okay, j m x naught I. So I here, j here, here it's j, here it is I. So what it is saying that in this case ith eigenvector is here, transpose of that. Here in this case jth eigenvector is here, here it is jth, here is ith. If m is symmetric, then this will be equal to that. Yeah. So hence, if we say this minus this will be equal to this, yeah, and that will be equal to 0, and this will be since k is also symmetric, this will be equal to 0. So k is symmetric, k is also symmetric. K is also symmetric. So that only means this will be 0, hence symmetric. So xi t x naught k x naught j will be equal to x naught j transpose k x naught I. This will be equal to this because k is symmetric. Hence if you have two vector, if you multiply one, after that one you transpose the vector and multiply, this will be same as this one if you interchange them, because k is symmetric. So this is the also property of the symmetric matrix. Yeah, so this is the thing. Hence this term from here it will be 0. So what you get is here everything will be 0, or you can write like this: x naught I t m x j, this is not is equal to, will be 0 since omega I is not equal to omega j. So as long as the natural frequencies are not the same, then this term is not equal to 0. Hence what we get is this. Okay. So what is the meaning of that? This is ith eigenvector, and this is jth eigenvector. And if you multiply two mass matrix, okay, so one comes before this, one the other comes after that, so such that this will be m, this is 1 by m, this is m by m matrix, and this one is m by 1. So total, or this makes a scalar. So what we see here is this equal to 0. Hence, mathematically we call that xi0, x naught I, and x naught j are orthogonal. With respect to mass matrix. with respect to M, with respect to mass matrix. Okay. Now, if the eigenvectors are orthogonal with respect to the mass matrix, can we say the same thing for the stiffness matrix? Yeah, and for that, this is important, right? So to begin with, how our equation was, remember we had k minus omega n square m, right? And then we wrote here x naught is equal to 0, right? 0 vector like this one. Now, if we put here the first eigenvalue, like ith eigenvalue, x naught I, this is ith eigenvalue, yeah. So then what do we get? We get k, then x naught I minus omega I square, then m, then we get x naught I. Okay, now we have the jth eigenvalue, we transpose it and we multiply here, so we get x naught j transpose k x naught I minus omega I square, we have x, this is just a scalar, so it will just go out, so this is x j transpose x naught m x naught I, right, will be, so this is equal to 0 and hence this is equal to 0. Now look at here, this says x naught I, okay, transpose m x naught j equal to 0. We can also have the, instead of ith one, okay, here instead of ith one, if we had taken jth here, jth here, and then multiply by ith here, we will get exactly the same thing. This also tells that if same logic you can use, if this is true, then this is also true. X naught j transpose m x naught I is equal to 0. So if this is true, we can derive just by interchanging I with j, you can find out that x naught j transpose m times x naught I equal to 0, and the same thing we have here. What we have, x naught j transpose m x naught I, and this term is 0, so this term is 0, hence this is 0. The whole thing is 0, this is not 0, but whole thing is 0, and hence this is also 0. Okay, so basically this also implies x naught j transpose k x naught I is equal to 0. Okay, so that means x naught I and x naught j are orthogonal with respect to m and k both. Okay, so this is the property of the eigenvector. Okay, so final statement here we will write that if x naught I and x naught j are two eigenvector, then m x naught I x naught j transpose is equal to 0 and x naught j transpose k x naught I is also equal to 0. Yeah, and hence this really means x naught I and x naught j are orthogonal to each other with respect to M mass matrix and stiffness matrices. That means all eigenvectors, again we have to say here that eigenvectors where when we derived it, we assume that omega I and omega j are not the same. So as long as the eigenvalues are not same, then we can say that the eigenvectors are orthogonal to each other, meaning that the meaning is this one. Okay, so this property of being orthogonal to each other is very interesting, and actually we can use it to make diagonal matrix, and we will do next time.